Welcome back. In this video, I'd like to run you through an example of a problem we as management engineers can do. Take note that this is a very simplistic example. There are other competencies that an ME student will have to learn that is not tackled here, but at least this example allows you to take a peek into what we teach our students. So let's take one example, UPS. UPS is a global leader in logistics, and as a global leader, what they are proud of is being able to deliver their packages to their customers as fast as possible. This means that they want to decrease the delivery time of their packages. This is important to them because this is one of the key metrics that they are using to achieve their goal of being the global leader in logistics. So the business problem that we want to be able to solve is to decrease the delivery time of the packages to their customers. Let's operationalize this problem. Essentially, UPS wants to start from a warehouse where all of the packages are, then given a subset of these packages, the company would like to deliver them to their customers in the shortest amount of time possible, and then go back to the warehouse to repeat the process. So how do we proceed? Let's simulate this on a very simplified map. Let's say you have this map of Fairview in Quezon City. This is where the warehouse is located. Then these three triangles are customers who need to receive their packages. In your analytic geometry, a map can be represented as a graph where the customers become the nodes of a graph, while the possible routes a delivery truck can take from one node to another are represented as a line connecting the two nodes. So this map can be simplified as this. So now we have a simplified map. The nodes represent the warehouse, and the customers, the lines connecting the nodes represent the routes the trucks can take. Now, let's tackle the business problem. If the objective is to start from the warehouse and then visit the customers and then return to the warehouse, what possible routes do we have? Before I continue, think about it. Again, our objective is to start from the warehouse and then visit the customers of the company and then return to the warehouse. If these routes were the ones that you thought of, then you're right. Well, there may be more. Let's look at these routes more closely though. Now, if you put a constraint that we should only visit the customers once, why should we go back to a customer, you can say? Then the first route is out of the question. In math, the routes that are remaining are what you call Hamiltonian cycles. These are routes that visit all nodes in a graph just once and return to the starting point. Now let's add another layer to the problem. What if we want to choose from among the remaining three, which is the cheapest, shortest, or most efficient route? Give you again time to think about it. Here's the solution. It seems out of the three, these two are the cheapest. And let's see now how this looks in our map. So here's the graph again, with the red route indicating the shortest route. Let's now overlay our map. We have now solved our problem. Using math, this problem of finding the best route to visit several destinations only once and return to the starting point to minimize travel time and cost is called the traveling salesman problem. Using this method, well, this is a simplified version anyway. UPS was able to save 10 million gallons of gas in a span of 10 years from 2004 to 2014. And just to also extend the problem, this is the basic principle that Waze uses. Not bad for a mathematician who has a great understanding of business, right? And this is what we do. data-driven decision making. At the start, we determine the business problem, then we model the problem, we gather as much data as we can, we simulate using technology, then based on the options that we generate, make the best decision, and then finally operationalize it.